Okay, welcome to our video on capacitance that we're running for while folks are out, and we may save for later. But this is intended to go along in parallel with our AP Physics course, and the students to this point have already some experience with determining electric fields in varying circumstances, varying geometries, including when you have a parallel plate capacitor where the distance between the plates is relatively small compared to their surface dimensions, so that the field between them is approximately uniform and close enough that we will pretend that it's uniform in size and direction. So, when we take a look at capacitance, we have from before, when we're looking at a capacitor, here we have, let's see, a sort of simple circuit setup here. This is our potential difference source, such as a battery, and it's hooked up to these two parallel plates of surface area capital A and of charge positive capital Q on the top plate and negative capital Q on the bottom. And they're producing an electric field E. We know that that field, from previous experience, we understand the field is going to be equal to the surface charge density sigma, or the Knight textbook uses eta instead, divided by the permittivity of free space, the vacuum permittivity. And so that surface charge density then is charge per unit area, so we substitute that in. And then we have our relationship between potential difference and the electric field. It's the negative integral of the field with respect to distance. Since the field is uniform as we go from the positive to the negative, the potential drop across that capacitor winds up being equal to the field times that distance, which I didn't mark. We can add that in ever so briefly to our diagram, like so. And so we see then that let's do this. So we see then that the potential difference across this capacitor is proportional to the charge on any one of the plates, and the remaining parts of this constant, that constant of proportionality between the accumulating charge and the potential difference, is related both to this fundamental property of the universe, our permittivity of free space, or vacuum permittivity, as well as the overall geometry of the capacitor, the gap between and the surface areas. And it's this constant of proportionality, or as we'll see in a moment, the inverse of that, that will become our capacitance. I do want to take a look at another geometry for a capacitor and see how it also has a charge and potential proportional relationship. And to do that, we can when we do that, we can sort of justify why we want to have this quantity that is this proportionality constant between them. So let's see, let's hook it up like that. All right. Let me label a few things in here. So what I'm going to set up is a coaxial cable for us. That is two cylinders. And let's throw those distances in here. And two cylinders, and the way we have this set up on this diagram, the outer cylinder is positively charged and the inner cylinder is negatively charged, and they would develop charge density of lambda, charge per unit length, between them. And when we take a look at that, and the field that that develops between those two charged bodies, we can also deduce the potential difference across how that relates to the accumulating charge. So we do that. We can run another integral here of our field with respect to distance again, and in this case we know that the field for a uniform charged cylinder, or anything with radial cylindrical symmetry, we've worked out previously with Gauss's law and with integrals, looking at Coulomb's law, that it has the form lambda over 2 pi epsilon naught r. And here we get to go from B to A. So, so our integral then, when we're doing the same potential integral as we did before, when we're working with the field for a cylinder here, and we're going from the outside to the inside, you get something of this form with the lambda dr over 2 pi epsilon naught r, where again we remember that lambda is charge per unit length, and this whole cylinder has some length L. So you do that integral, and you know with an integral with that's of where the integrand has 1 over the index you're integrating by, you're going to get natural logs. And we've got the way that our signs work with this. You run that through, and you're going to get all the lovely constants out front. And then a natural log of, let's see, it's going to be B over A, the way we've got that worked out. So you get, that's supposed to be a capital L here. You again get a proportional relationship between the charge on one of the plates. Here it's a cylinder rather than a flat plate. And some fundamental constants, as well as relationships to the geometry, the inner and outer radii of the cylinders, a 2 pi in there popping out, and a 2 pi L in there popping out from the length of our cylinder and the circumference relationships. So it makes sense. It's justified that we want to characterize what this proportionality constant is that has a geometrical basis in it. So we determine, we're going to call this thing capacitance. We'll talk about it as like the capacity to hold charge. And so we define capacitance as the relationship between the proportion between the maximum charge that will accumulate on the positive plate of a capacitor and the potential difference between them. And so it has units of coulombs per volt, which we call a farad after Michael Faraday, who we haven't talked about in great detail in this class yet, but you've encountered him in chem classes as the person who figured out hydrolysis of water into hydrogen and oxygen, and has explored a lot of the relationships between electricity and magnetism, came up with the concept of the field and a variety of other accomplishments. So that's our beginnings here. So this is capacitance is this proportionality constant between charge on a capacitor and the potential difference between them. So that charge, the charge does not show up all at once. It takes some time to accumulate. You set this up, and let me give us some space here. You set this up, and the charge will gradually gather. You hook up a capacitor to a battery, to your potential difference source. It's going to gradually gather on the plates until it reaches a maximum value. And so we know that we're doing work to move that charge through an electric field through a potential difference. And so we know, given that, that the we're going to have a relationship. We're going to be building up a potential energy as we add more and more charge to the plates. And so we can start to add them together, integrate all that up to determine how much potential energy you have stored there. And so we have to do this as an integral. And so we swap in our definition of capacitance here. For the potential difference, and rather than looking at the maximum charge to start with, we're going to start with no charge accumulated on the plate and then go to the maximum charge. So that's a 0 down here. And so you do the integral and standard power relationship. Gets you the potential energy stored in a capacitor and its relationship to that maximum charge and the capacitance. But the maximum charge isn't necessarily the thing that you've got memorized or measured easily, but you do have standard ways of measuring potentials, and you have capacitance determined by looking at the geometries of the capacitors. So we can express this in terms of capacitance and potential difference instead. And so you do that, and you say, okay, Q equals C over delta V. Or sorry, no, that's my mistake. Q equals C times delta V. So you get capacitance oh, I totally made an error here. Well, we'll have to reshoot this later, but our potential difference that we had before, okay, so let's go back here for a sec. It was our potential difference that we saw before was 1 over C, Q over C rather. So that leaves our capacitance as our potential energy for the capacitor as 1/2 Q squared over C. When we do this substitution, then we're left with 1/2 C times potential squared for the capacitance, or it's also 1/2 maximum Q times potential, and that sort of makes sense, that it's not our standard relationship between potential difference and potential energy, where you're multiplying by the charge that's there at the moment, because here the charge has been changing with time as it was built up. So that capital Q is not the charge at any instant that has moved across that potential, but rather 1/2 of that capital Q is sort of the average charge that has moved across that gap to build up that total charge of capital Q. All right. Let's see. There are other things we can do with this. And we can look at circuits that involve multiple capacitors. And when we do, they can be arranged in a few different geometries. Some of the simplest ones would involve capacitors that are arranged in what we say is parallel versus capacitors that may be arranged in series. So in parallel, if a circuit element is in parallel with another circuit element or a collection of circuit elements, it means that the current or the charge can flow through any of those paths that are in parallel, but it's got to start going through one common location and end up going through another final common location. So these two paths are in parallel to each other. Whereas circuit elements in series, the current has to flow through one and another, and there's no opportunity for it to divert from that path or the collection of elements that are in series. So we find that it's useful to evaluate properties of the circuits by looking at these arrangements and seeing what would be the equivalent of what would the single capacitor equivalent be for the function of all of those capacitors that are arranged together. And to determine how these work, we have to invoke effectively what are some conservation laws. They were determined around 1845 by a fellow by the name of Gustav Kirchhoff, or Kirchhoff. So Kirchhoff's laws, he's got actually two different sets of laws. He's got Kirchhoff's laws for simple circuits, and he has a set of additional laws for interpreting spectral lines, which are not in the scope of this course. So Kirchhoff's laws run like this. There's a law that is essentially functionally equivalent to the law of conservation of energy. We consider our circuit to be a closed system so that energy is not leaving or entering the wires. And neither is electrical charge. So he has laws that are related to conservation of energy and that are related to conservation of charge. The one that's related to conservation of energy we call the loop law. And the loop law goes like basically the total potential difference around a complete loop must be 0. So delta V is 0 around a complete loop. And that should make some sense because you get back to your starting point and the potential you have at that location should be the potential you had at that same location before, so the potential difference should be 0. You don't gain anything by cycling around, basically. Not in total. You may gain and lose stuff along the way, though. The conservation of charge law is known by a few different names. It's known as the node law or the junction law. I'm going to call it the node law here. And it basically says that the charge or current entering a node equals the charge or current leaving that node. So we use these to explore the relationship between collections of capacitors and the equivalent substitution of a single capacitor. So let's see how this goes. Let's start with an arrangement of capacitors in parallel. So I'm going to sketch out what this may look like. And I'm going to draw here two capacitors and then a third one, which I'll label as my nth capacitor. Okay, so in an arrangement of capacitors in parallel, we've got here our battery or our source of potential difference, and the current can go, the charge can go through capacitor 1, capacitor 2, any number of capacitors, the final one of which I've labeled capacitor N. And charge will accumulate up to some maximum value of Q1, Q2, and so on to Qn. The potential difference across each of these is potential difference 1, potential difference 2, 3, and all the way up to potential difference n. So we know from the node law that total charge Q naught has to equal Q1 plus Q2 plus all the Q's up to Qn. Whatever leaves that top part of the battery there, the positive charge of the battery, has to spread out across all the other capacitor is on its way back home to the bottom end of the battery. And so if we use our relationship for capacitance, we know that charge is equal to capacitance times the potential difference. And the idea here, again, let's make this explicit with a diagram. Is that we're swapping out all those capacitors for a single equivalent capacitor. I've labeled CEQ and then the two parallel lines to indicate that this is for a parallel arrangement of capacitors. And so that equivalent capacitor would accumulate the total charge Q naught. That's going to equal the sum of all these individual charges across all these individual capacitors. And we also know that, so we know that Q is equal to capacitance times potential difference. So we get to say, all right, so Q, so C equivalent parallel is Q naught times that potential difference. Q1 is equal to C1 times its potential difference. Q2 is C2 times its potential difference. Qn is Cn times its potential difference. Like so. But we also know that the potential difference, the loop law tells us that we go around a loop that just goes through one of these capacitors, but also goes through the battery. The potential difference has to add up to 0. So that means that however much potential difference we add going through the battery, we have to lose going through that capacitor. We have to lose going through the equivalent capacitor as well. It's the same potential difference across each of these capacitors. V naught here going through that capacitor is the same as V1, V2, Vn. So, our loop law here gets to say that delta V naught is delta V1 is delta V2 is delta Vn. And so in that case, all these, there's the same potential term in every stinking one of these terms here. They all get to cancel. And so we're left with our equivalent capacitance is just equal to a simple sum of all the individual capacitances. So we can express that in series notation and say, I'll box this off in the corner here, C equivalent parallel is the sum from index I equals 1 to n of C sub I. So yeah, so here's our series notation equivalent of, over here is the equivalent of this statement on the left side of your screen. So we've got that. So one more thing in this video, and that's, well, what about capacitors in series and their equivalent capacitance? So let's do that. So I'll do a quick sketch here. Okay, so in this case, where we've got all of these capacitors in series, then, well, the way we look at this one, the loop law is going to tell us when we swap them out for a single capacitor that the loop law here tells us that all of these individual potential differences are going to add up to be the same amount as the potential difference across our battery. So we can write that down. So delta V naught equals delta V1 plus delta V2 plus delta Vn. And so we express that in terms of capacitance. We can say, okay, so C equivalent sigma for series over Q naught is equal to C1, no, other way around. Q naught over C equivalent series is equal to Q1 over C1 plus Q2 over C2 plus Q over N over Cn, like so. But the node law tells us that the charge that goes through all here has to be equal to the same charge. The charge is conserved. So as the charge that accumulates on any one of these plates winds up being the same size charge on any of the ones in sequence. So the node law, or conservation of charge law, tells us that Q naught is Q1 is Q2 is Qn. And so that means that all of these charges get to cancel. And we're left with a law that goes 1 over the equivalent capacitance in series is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. And I'll write this in series notation as well, but I need to make myself a little more space for that. This is a little more complicated. So we can say C equivalent in series is in big parentheses equals 1 to n 1 over C sub I. So it's the inverse, the reciprocal of the sum of the reciprocals of all of the capacitances. So this should make a little bit of sense that you keep on adding more capacitors here, you're reducing the overall capacitance by doing so. And whereas if we added more capacitors in parallel, we're increasing the overall capacitance. And if we think about this from a geometrical sense, and go back to the beginning of all of this, and we said, okay, capacitance gets to equal Q over potential, but that when we when you put in the potential for a parallel plate capacitor, you wind up with it equaling epsilon naught A over D. And so it makes sense that if you're adding more of them in parallel, that's effectively adding like more area for your parallel plates. So you would expect that it would get bigger in that way. Whereas if you're adding them more in series, it's sort of like making the distance between each of the plates sort of in total smaller. There's less overall gap between the topmost plate and the bottommost plate. You've got these stack of plates in parallel that you're working together. So that's it for what we've got for now for capacitance.